Hi, this is Antti Vanne from OwnSurround, and this is a tutorial for scanning a human head so that it is accurate enough for audio simulations. And we use a structured light scanner, David SLS2 in this case, and this is the scanner's own software tool. And in order to create accurate head-related transfer functions, also known as HRTFs, we need a resolution of about 5 millimeters in the face and around 1 to 2 millimeters in the ears. So we use two kind of scanning resolutions. And first, we calibrate the scanner with the 240 millimeter target, so 240. And for this larger scan, we use the whole length of the scanning rig's rail to get a large enough angle between the projector and the camera. So move the camera to the end of the rail, align it, and go to the calibration settings here. Use the 240 millimeter target and just go ahead with the calibration. And for the head and shoulders, you can get a nice geometry with just 8 scans, where there is enough overlap and enough data around the ears to later align the higher resolution ears to the head. And we usually instruct the scanned person to face the camera first and then turn around in 45-degree steps. Here you can see an example of 8 separate scans. And first we need to coarsely align them together. So we start with the front-facing scan and align a scan at a time, going from front to the back. Okay, now we have aligned one side of the head, and then we continue aligning the other side. So now the 8 scans are coarsely aligned to one another. And now that we don't use any equipment to keep the target from moving, it's very useful that people turn their heads between the scans, and that you can see here that the nose and the chin is not very well aligned. And that's why we need to align shoulders and the head separately to get a good quality mesh. So next we need to cut off the head and save both the head and shoulders scans to separate files, and then realign them, the head and shoulders, separately, and you'll see that the quality is improved a lot. Okay, so now the head scans are aligned separately from the shoulders, so you can see that that's quite an improvement in the alignment. And now you can run the fine registration for all the scans. Okay, when they are aligned, you can next fuse the scans together, and you can use a resolution of about 1 millimeter is pretty good, and for the sharpness you might need to test a couple of values and close the holes and run the fuse. So this is a pretty good head scan. And now usually when people have dark hair, it's better to use a cap so you don't have this kind of things on top of the head that are just due to not having enough data from the top of the head due to dark hair. And then export this fusion result to a file. And now we do the separate alignment to the shoulders. And after we've aligned the shoulder scans, you can fuse these scans together. And for the shoulders, you can use the minimum resolution and the minimum sharpness, and you don't have to close the holes. They are closed further down the process. And then just click fuse. Okay, and now the shoulders are fused together, so they should look something like this, and then you save the shoulders to a separate file. And for the ear scans, you need to recalibrate the scanner using the 120mm target and 120mm here in the calibration, and then recalibrate. For the ear scanning, this has to be done quite accurately, since we need the 1 or 2mm resolution in the ear. So we start with scan, say about 45 degrees from the head, and then go on, and then we need to tilt the head back and forth. And during the scanning, you have to check which parts of the ears has been scanned and which haven't, and instruct the target accordingly to get data from all around here. So you need to tilt the head, the side and another, and maybe turn it a bit further and do the tilting again. Take the last scan from behind the ear. So this is the scan sequence you need to go through to get enough data for the ear. And again, with the ear scans, we take a reference scan which is taken from the side. It could be, for example, this one, and we start aligning the other scans to this one reference scan. And first we do again the scan alignment coarsely. Okay, now we have the scans coarsely aligned to one another, and of course, since the head was tilted during the scanning, the shoulders here are in different places, and that means that the alignment is not very good in the ear either. So now we have to get the region of interest separately here. Take a couple of centimeters around the ear and pay attention to the neck muscles over here that might have moved a bit, so you don't want to take too much of that area. So now we run the alignment again. So now we have aligned the ear scans together, and you can see that the alignment is much improved. And then we go to the global fine registration and run that. Keep in mind that you need to instruct the target during the scanning process to turn the head and tilt the head so that you get enough data, especially from here and here where there are cavities that what we are interested in. Now that the ear is aligned, we again fuse the different scans together, and again we might need to test a couple of values for the sharpness. So now we have a pretty nice ear fused here. We have some extra surface over there, but it doesn't matter, so just save this again, the fusion result, to a separate file. And then we do the same thing for the right ear. And here we have fused the right ear together. And we also save this one to a separate file. And now we start putting all these pieces together. So we take the shoulders, we load the head, and we load both of the ears. So here are all the 4 pieces that we need to put together. Next we remove the unneeded parts from the ears and align the ears to the head. Okay, now the ears have been aligned to the head and they look quite nice. Now you have to remember that we used the close holes option when we fused the head, and this means that it's a closed surface. So now you want to remove this part of the head surface. And also you can remove the artifacts from the hair. Okay, this is starting to look like a person. So next we just need to get rid of the sparser ears. So that means that we have to cut holes for the ears that have the better resolution. And now finally we put this together. Choose a suitable resolution around 1 millimeter, good sharpness value, and close holes, and click fuse. So this is what we get after the fuse process, fusing all the pieces, the head, the shoulders, and the separate ears together. And we can see the ears are modeled nicely. There is the enough resolution for HRTF simulation. In fact, now the resolution, or the number of triangles, which you can see here, is even a bit too much, because we usually want to have something around 200 or 300,000 triangles per the whole mesh for the simulation. So next we need to turn this mesh to the simulation mesh. And we again save the fusion result to a separate file. So now that we have the mesh from the David SLS software, we need to clean it up a bit and then remesh it for the simulation purposes. I'm using Mesh Lab here, and what we need to do here is get rid of some separate parts that might be in the end result of the fusing process of David's software, as you can see some of them here. Remove isolated pieces, and next we want to remesh this, and we use net again for that purpose. So we want to save this mesh in STL format. In NetGen we load the geometry, and we need to check that the geometry is okay. In case of any errors, they are displayed on this window. Then we need to set suitable parameters for the meshing. The last step we want is mesh the surface, and regarding the mesh size we use maximum mesh size 2.5 and minimum 1, and then just generate mesh. And finally, here we have a mesh suitable for simulations. You want to check the shoulders, just that there are not any very deep cavities in here that might affect the simulation. And then again, of course, that the ears, both ears are fine. They have enough resolution. Finally, save this or export this mesh in STL format.